Hello, dear students. Namaste. This is Dr.Kemparaju. Welcome to the video class. So, in this class, we're going to learn what is a subgroup with certain examples and so the necessary and sufficient condition for a subgroup. Definition for a subgroup: a non-empty set H of a group G, star is said to be a subgroup of G. When we can say it is H is a subset of G and H itself is a group. So when you can say this H is a subgroup of a group G when it is a subset of a group G and H itself is a group. You know, the group means it satisfies closure law, associative law, inverse law and identity law. So that note will consider that every group is a subgroup of itself, and the set which contains an identity element E is also a subgroup of a group G. It is. So these two subgroups, the set itself, whatever the group itself, and the set which contains E, these two subgroups are called trivial or improper subgroups. And the other subgroups, suppose if they exist, then they are called non-trivial or improper subgroups. Normally, so sometimes it may exist, or it may not exist in this. So the identity element of a subgroup is same as the identity element of a group in G. Whatever the identity element exists in the group G, the same identity element should be exist in the subgroup also it is. And the inverse for each element of a subgroup is same as the inverse of the each element so in the group. So exist whatever this element, so we are taken on the set H, so which are derived from the group G. So whatever the inverse we are going to find in the subgroup H, the same inverses should be, so there is the same inverses should be exist in the subgroup also. Here we are going to learn what is certain examples in this. So the additive group of even integers, you know that even integers are nothing but 0, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. These are all the even integers. It is a subgroup of additive group of all integers. Integers is nothing but 0, plus or minus 1, plus or minus 2, plus or minus 3. These are all. So this even integer is always a subgroup of a group of integers under the operation addition it is. And here learn this. So that is an example for an infinite subgroup. So here we are going to learn, so what is an example for a finite subgroup of a group. So I prove that H contains 0, 2, 4 is a subgroup of a group G which contains 0, 1, 2, 3, 4, 5 under addition modulo 6. So that means here we have to prove that H is a subgroup of a group G under the operation addition modulo 6 it is. So for that it is given G is a group. So for that, so whatever the elements are there in the set H, you construct the Cayley table for that. That is for 0 to 4 it is. And also it is clearly we can say that 0 to 4 are the elements which are also present in the set G. Hence we can say that H is a subset of a set G it is. And construct the Cayley table. So you know how to construct the Cayley table. So that is in the first row 0 to 4, and in column wise also you can write 0 to 4 the elements of the set H it is. While adding the elements, 0 with the 0 it gives 0 only, 0 plus 2 is 2 only, 0 plus 4 is 4 only, that is in the first row. And in the second row 2 plus 0 is 2, 2 plus 2 is 4, 2 plus 4 is 6, but 6 under addition modulo 6 it is 0. When it is divided by 6, the 0 is the remainder. And in the third row 4 plus 0 is the 4 and 4 plus 2 is 6. Again when 6 is divided by 6, the remainder is 0, and 4 plus 4 is 8. So when 8 is divided by 6, the remainder is 2 it is. This is what the table is called Cayley table for the set H equals to 0 to 4. Now we have to say this is a group. So to prove this is a group, we have to show this satisfies closure, associative, identity and inverse laws. The first thing is the closure law. Observe the elements in the table, so which we got 0, 2, 4, 2, 4, 0, 4, 0, 2. These are all the elements in the set H. So therefore we can say that is closure law satisfying. So that means all the elements in the table are in the set H, hence we can say that closure law satisfying. So to prove an associative law we need three elements. Say it is 0, 2, 4, only the three elements we have. We take all these three elements. So and one other thing is we change the brackets. In the left hand side we put the bracket for 2 and 4, and in the right hand side we put the bracket 0 and 2 it is. So while simplifying this, 0 plus, when you add 2 with 4 it becomes 6, but under addition mod 6, when it is divided by 6 it becomes 0. Again in the right hand side, so 0 plus 2 is 2 plus 4 it is. And then in the next year 0 plus 0 is 0, and in the right hand side 2 plus 4 is 6. When 6 is divided by 6, 0 is the remainder. So hence the LHS is same as RHS and 0 is an element of H. We can say that associative law satisfying. The next thing is the identity law. So you know the under addition identity is 0. Simply you can say that 0 is an identity because 0 is an element belongs to H. But also we can say that the row headed by 0 is same as the topmost row. Observing this, so there is 0, 2, 4 is same as the same over this the topmost row 0, 2, 4 which we got by adding 0. So therefore 0 is the identity element. Next is to find the inverse element. So inverse for each element. So that inverse we can find from the table. So from the table observe that in the first row the identity is 0 in the first element, and in the second row we got in the third place, and in the third row we got in the second place. So as 0 we got in the first place by adding 0 with 0. So therefore inverse of 0 is 0. And in the second row, while adding 2 with 4 we got 0. So therefore inverse of 2 is 4. And in the third row, when you add 4 with 2 you'll get 0. So therefore for inverse of 4 is 2. This is how we can find the inverse for each element from the table. So hence we can say that so there is inverse law satisfies. So after satisfying all these four laws, simply we can say that H is a group. Hence we can say finally we can say that H is a subgroup of a group G under addition mod 6 because it is a subset as well as a group it is. So this is how we can prove. So whatever the set is a subgroup of a group G under given operation. So here one more example, that is H is 1, 2, 4 is a subgroup of the group G 1, 2, 3, 4, 5, 6 under multiplication mod 7. Here also you can say that clearly H is a subset of G because the elements 1, 2, 4 are derived from the set G. So hence we can say that H is a subset of G. And finally this 1, 2, 4, 1, 2, 4. So for that we construct the Cayley table. So we construct the Cayley table. So for that, that is again, so it is defined under multiplication mod 7. So 1 into 1 is 1, 1 into 2 is 2, 1 into 4 is 4. Similarly in the second row 2 into 1 is 2, 2 into 2 is 4, 2 into 4 is 8. But when 8 is divided by 7, 1 is the remainder. And 4 into 1 is 4, 4 into 2 is 8. When it is divided by 7, 1 is the remainder. 4 into 4 is 16. When it is divided by 7, so that is 2 is the remainder. So then similar to that, we can say that the closure property satisfies because all the elements in the table are also in the set G. So therefore closure law satisfies. To prove an associative law, we take all these three elements 1, 2, 4 and just to keep changing the bracket. On the left hand we put the bracket for 2 and 4 and in the right hand we put the bracket for 1 and 2. So while simplifying we got 1, so which is an element of H, hence we can say this associative law also satisfies. So after satisfying associative law, the next thing is so identity law. So the row headed by 1 is same as the topmost row. Again, observing this table, we can say that 1 is an identity. So here also we can say this under multiplication usually 1 is always an identity. So hence the identity law also satisfies. And from the table we can observe the inverses for each element. So here 1 is the identity we observe. So in the first row 1 we can find in the first place, and in the second row we can find in the third place, and in the third row we can find in the second place. So 1 here we got by multiplying 1 with 1, so therefore inverse of 1 is 1. And when we multiply 2 with 4, we got 1 in the second row, so therefore inverse of 2 is 4. And finally in the third row, when we multiply 4 with 2, we got 1, so therefore inverse of 4 is 1. So hence we can say that, so it satisfies what that inverse law it is. So after satisfying all these 4 laws, simply we can say that H is a group. So H is a group and H is also subset of G. So hence finally we can conclude that H under multiplication mod 7 is a subgroup of a group G under multiplication mod 7. This is how we can prove that whatever the given set is a subgroup of a group. So in this, I think these examples are enough for your examinations and all. So the next thing is, so we're going to prove what are the necessary and sufficient conditions for a subgroup. So normally to prove this subgroup, we know that H is a subset of G, that is initially, and then we have to say that H itself is a group, but not necessary to prove always it is a group. So there are certain necessary and sufficient condition easily can prove that is a subgroup. In the theorem, that is we're going to derive this theorem 1, a non-empty subset H of a group G is a subgroup of G if and only if for all AB belongs to H, A star B belongs to H, and for all A belongs to H, A inverse belongs to H. That means it is given H is a subset of a group G, and we can say it is a subgroup of a group G. So when these two conditions are satisfied, that means the first condition is nothing but closure law, and the second condition is nothing but inverse law. Or the vice versa, that is in the converse. Suppose if these two conditions are given, the closure and inverse law, then we have to say this H is a subgroup of a group G. It is. That is the sufficient condition. That means to say that H is a subgroup of a group G, it is enough to say that if satisfies closure law and inverse law it is. Now we are going to prove this, the necessary condition. It is given H is a subgroup of a group G. So we have to prove that H satisfies these two laws. So we know that when H is a subgroup of a group G means H itself is a group. H itself is a group means it satisfies closure as well as inverse law. So therefore by closure law we can say that first condition will obtain, and from the inverse law we can say that the second condition also will obtain. That is for all AB belongs to H and A star B belongs to H, and for all A belongs to H, A inverse belongs to H. This is what simply you can say that necessary condition, nothing in this case. By group definition itself we can say that closure and inverse law satisfies. And the next thing is the sufficient condition. In the sufficient condition, we take this for all AB belongs to H, A star B belongs to H is given, and for all A belongs to H, A inverse belongs to H is also given. These two conditions are given. So that is closure and inverse. Now the next thing is we have to prove H is a subgroup of a group G. So to prove that H is a subgroup of a group G, so it is enough to prove that H itself is a group, because it is given H is a subset of G in the statement only. So therefore it is enough to prove that H itself is a group. That means H satisfies all 4 laws. From the data itself we can say that from the first one we can say the closure law satisfies, and the second one we can say that inverse law also satisfies. And by replacing B by A inverse in the first equation, that is in place of B I'll write that A inverse. So in that case we'll get A star A inverse A star A inverse, always we know that it is equals to E, so that is an element of H. So that means E is an identity, so identity exists in H, so identity law satisfies. So identity satisfies, closure satisfies, inverse satisfies, only thing is associative. So that is A star of B star C, that is equals to A star B of star C, that holds always in the set G. The same elements if you are taken under set H, the same under the same operation, so that A star of B star C, that is equals to A star B of star C also holds good in H also. So hence we can say that associative law also satisfies. So it satisfies all the four laws. So if satisfies, then we can say that H under the binary operation star is a group. H is a subset of G and H is a group. Hence finally we can conclude that H comma star is a subgroup of a group G comma star. That means easily we can say that H is a subgroup of a group G only when closure and inverse law satisfies. That is our sufficient condition. And we can further simplify this theorem 1 by combining closure and inverse law, so as a single statement. So here observe that, so the statement states that a non-empty subset H of a group G is a subgroup of a group G if and only for all AB belongs to H, A star B inverse belongs to H. Instead of those two conditions, here we combine them. So that is B inverse we can find in the same statement, that is in the closure property, A star B inverse belongs to H. That is, it is enough to say that whenever A star B inverse belongs to H, then H is a subgroup of a group G it is. As similar to that our previous theorem, here also we can prove that necessary conditions simply. So that is given H is a subgroup. That means H itself is a group. H is a subgroup means by definition we can say that H is a set itself is a group. Therefore by inverse law, whatever the element, so for all B belongs to H, we can find its inverse B inverse in the same set H. And then by closure law, if we take the two elements, that is A and B inverse is also an element of H we proved. So A B inverse belongs to H, we can say that A star B inverse belongs to H. That means for all AB belongs to H, A star B inverse belongs to H. So that is what the necessary condition. The next thing is the sufficient condition. It is given that data it is for all AB belongs to H, A star B inverse belongs to H. That is the data. Using this condition, so we have to say that H is a subgroup of a group G. It is given H is a subset of G, so hence it is enough to prove that H is a group. That means we have to say that H satisfies all four laws, that is closure, associative, inverse and identity. So for that we will going to replace, so in the first equation A by B, in place of A I'll replace B, we'll get B star B inverse. What is B star B inverse? Usually we know that identity E. So the identity element exists in the set H, hence we can say that identity law satisfies. We know that identity exists in the set H, so therefore we'll replace instead of A as what? E in the first equation. In the first equation we're going to replace A by E, so we'll get E star B inverse. Whenever you apply identity on any element, we get the same element. So therefore E star B inverse is nothing but B inverse only. That is B inverse belongs to H. So easily we can say that B inverse belongs to H means the inverse law satisfies. So identity satisfies, inverse also satisfies. Then we're going to replace B by B inverse. You know that B inverse exists in the set H. We'll replace B by B inverse in the first equation. So that is A star B inverse of inverse it becomes. When we replace B by B inverse, already inverse exists, so therefore we can say B inverse of inverse. But B inverse of inverse is always nothing but B. So therefore A star B belongs to H. So there is nothing but a closure law also satisfied. So to prove an associative law, just like your previous theorem, here also we can say that A star of B star C equals to A star B of star C holds good in G. So the same thing holds good in H also. So hence we can say that H satisfies associative law. So H satisfying closure, associative, identity and inverse. So therefore we can say that H is a group. H is a group, H is a subset of G. So finally we can conclude that H comma star is a subgroup of a group G comma star. So that is, so here onwards, here it is enough to prove that. So that is H is a subgroup of a group G only when for all AB belongs to H, A star B inverse belongs to H. This is only the condition is enough to prove H is a subgroup of a group G. And one more theorem, yeah, we have. So that is show that the intersection of two subgroups of a group G is again a subgroup. Suppose if you take the intersection of any two subgroups, that is again a subgroup. So for that, you consider H and K are the two subgroups of a group G. So H is a subgroup of G and K is also a subgroup of G. So if their subgroup means, then it's a group. Group means it should contain at least one element, say it is E. So E belongs to H and E belongs to K. So E is the common element of both H and K. So hence we can say that E is also an element of H intersection K. So that we are going to prove that H intersection K is not a null set. It's a non-empty set. It should be a non-empty set. So the next thing is we have to prove H intersection K is also a subgroup of a group G. So for that, to prove that H intersection K is a subgroup of a group G, as like your theorem 2, it is enough to say that whenever A star B inverse belongs to H intersection K, we can say that H intersection K is a subgroup. So for that, we'll take any two arbitrary elements for all AB belongs to H intersection K. That is, AB are the common elements of both H and K. So that means it belongs to H as well as it belongs to K. So that is, for all AB belongs to H and for all AB belongs to K. But H is a subgroup, K is a subgroup. H is a subgroup means, again by theorem 2, we can say that A star B inverse should belongs to H. K is a subgroup, so we can also say that A star B inverse also belongs to K. So that means A star B inverse is the common element of both H and K. So hence finally we can say that A star B inverse is also an element of H intersection K. So therefore H intersection K is also a subgroup of a group G. This is how we can prove the things. But intersection of any two subgroup is always a subgroup of a group G. Is it the union of two subgroup is again a group? No. The union of two subgroups of a group need not be a subgroup. It may be, may not be, it depends on the given set. So that is, the union of two subgroups of a group need not be a subgroup of a group G. For example, if it is the set of integer is a group under addition, and 2z also 3z under the same binary operation under addition by the two subgroups. 2z is also a subset of z, 3z is a subset of z, and it satisfies all the four laws. So therefore we can say that 2z and 3z are the two subgroups under the binary operation addition. Suppose if they take this union, 2z union 3z, but it is not a group, because if you take 2 is an element of 2z, 3 is an element of 3z. So the 2, 3 are belongs to 2z union 3z. But under addition, if you add them, it gives 5. But 5 is not the element of 2z union 3z. 2z union 3z, only it contains the elements which are multiples of 2 and multiples of 3, but not 5. So therefore, the union of two subgroups need not be a subgroup of a group G. So these are the certain theorems under these subgroups. So we're going to conclude this subgroup of a group G. So I hope you all understand. So whatever the things I explained here.